So, good morning, everyone. This is a battery thermal modeling webinar hosted by Techlanz. And today, me and my complete team, we are presenting to you battery thermal modeling session. So, what is the agenda for today? So, in today's agenda, we'll be covering battery thermal management fundamentals. We will see what is the heat generation mechanism inside a cell. We'll also see what is a battery modeling approach, different modeling approach which are there in the industry, people use in the industry. What's the battery thermal system design process? We'll also have a MATLAB demo today. So in that you will learn how the uh, thermal modeling is done inside a MATLAB or Simulink environment. Okay, because we want to choose a tool to demo it also, right? Then we'll have a small overview of Techlanz at the end for 5 minutes. So today is very core technical session, very technical session. We'll go in detail of equations, we'll go in detail of mechanisms of heat generation, right? And we'll also demonstrate you how it is done, right? So looking forward to your 100% participation, right? Let's go one by one. So first of all, you know that, or you have seen that the thermal management system can become very complicated, right? For the air cooling or as well as a liquid cooling. So there are multiple components inside a liquid cooling system, be it evaporator, condenser, right? Liquid cooling plates. Similarly, for air cooling also, you have to take care of multiple things, like be it blower, PCM, and so on and so forth. But there are fundamental reasons you should understand what point of time you should choose a air cooling system and what point of time or what are the conditions you should use the liquid cooling system, right? So unnecessarily, if you choose a liquid cooling system over air cooling system, you'll increase the system cost and system weight, right? So in this today's session, you'll learn what are the decision factors or how you can make a better decision towards your cooling requirements, right? So what is thermal management requirement? So everyone knows that a cell cannot operate beyond a certain voltage, cannot operate below the certain voltage. Similarly, holds true for temperature as well. So temperature wise, cell has a sweet spot of operation. So it should not be operating above certain temperature, should not be operating below certain temperature. But why is that? Right? Have you ever thought about it? Why you should be operating a cell on a certain temperature zone? It's only thermal runaway or something else is also happening. So we'll go deep dive in today's this one, that why these limits are set and why this impacts the cell performance, right? So first and foremost, this graphs, if you see, let me use pointer over here, right? So if you see this graph is for the cell capacity. So if you know that this is basically SOC, right? This capacity of a complete cell means this is a SOC, this is voltage, and area under the curve of SOC OCV curve gives you the total capacity, total energy of the cell, right? So if you see this at very low temperature, which is minus 20 degrees centigrade, the overall capacity of a cell degrades very much, right? So this is very low capacity. If you see minus 10 also it's less, then 0 degree is slightly better. If you see when you keep on increasing the temperature, the energy of a complete cell increases, right? So energy output of a cell increases. So based on this graph, you think, okay, I should not operate in the lower temperature, right? But then if I'm getting a higher energy at higher temperature, then we should be using the higher temperature, right? But then what's the issue? If you're getting a higher capacity from a higher temperature, then you should be using higher temperature, right? This is the first thought process. You can use the chat box in the question answer sections to post your comments, right? Let's make it very interactive session. So you will also learn and we'll also see your comments and we will brainstorm around some points. So basic thought comes, right? But why this is, then we should be operating at 50 degrees, 60 degrees centigrades and all those things. But there are the fundamental challenges associated with this. This particular graph is for any given point of time when you compare the capacity of a cell for any instant for a higher temperature versus lower temperature, right? because of resistance change. I'll talk about resistance change in much more detail. So what happens at lower temperature, the viscosity of the combined electrolyte is very less. The chemical reaction, if you know Arrhenius equations, the rate of equation is very less, right? At higher temperature, the rate of equations is very high. Electrolyte density, viscosity is also comparatively lesser, right? So that time it promote the movement of ions and electrons inside the system, right? And because of about the activation energy of chemical equations, right? So because of higher temperature, the chemical reaction also happens much more faster. At sub-zero temperatures, the electrolyte almost freezes, right? The viscosity and density becomes so high, it actually does not promote the movement of ions and electrons inside the electrolyte. And the chemical reactions also does not happen. So this is the reason why the capacity increases when the temperature is higher. But because of this higher energy which is available for the chemicals, right? The degradation also happens much more because now all the chemicals are reacting at very fast reactions, right? There is a fast reactions which are happening inside the chemical system. Because of which what happens, the degradation also happen much more faster. So if you see this over the period of time, if you see with respect to the temperature, if you see the relative resistance, okay, you can post your questions in the chat box. If you see with respect to time, the resistance keep on increasing. If you see, so if you see this is time, this is resistance, and this is for 55 degrees centigrade. If you are operating, keep on operating your cell at 30 degrees centigrade, so the resistance increase is very nominal. But if you keep on operating your cell at higher temperature, with respect to time, the resistance keep on increasing and eventually the capacity also degradation happens. I'll talk about in the next slide. But now if you see this, right? If you see this slide, this particular thing, this is very evident from this graph itself. The capacity degradation at 25 degrees centigrade with respect to first cycle and 2250 cycle, it's very less. But if you see the temperature, the capacity degradation, right? Because when the cell resistance is increasing, the degradation also will be having faster, right? So if you see that the degradation of the capacity is much more higher when you keep on operating at high temperature, right? This is clear. So that means at any given point of time, if you want to operate higher temperature, which is okay, it will give you at that point of time higher capacity. But over the period of years, the side reactions will happen because of higher electrochemical reactions. Many side products gets created. The electrolyte dissolution happens because of which what happens that you get so many byproducts in the chemical reaction. They create the resistance inside the chemical paths, which increases the resistance and degrade the capacity over time, right? This is something very important. Now that means we have some kind of trade-off, right? So when you operate at higher temperature, you get the higher capacity, but if you operate at higher temperature, you get the life degradation, right? So there is some kind of trade-off if you see over here in this graph, which is very beautifully mentioned. If you see that if at lower temperature, your capacity, right, or battery life is very good, right, but the capacity is very poor if you operate at low temperature. So your battery life become very good, but the capacity which you extract from of the battery, instead of for suppose a 5 ampere hour, you only get 2.5 or 3 ampere hour. Whereas if you keep on operating your battery at high temperature, you see that you get very good capacity, but you get very bad battery life, right? So you may get around, instead of 5 you get 6 ampere hour, but your battery life instead of 1000 cycles become 200 cycles only, right? So that's why there is a sweet spot. The trade-off is there in between 20 degree to 30 degree or 35 degree depending on chemistries with LFP, NMC or sodium ion or solid state battery. This temperature zone changes, especially for solid state. This temperature zone is much more higher. We'll talk about it later, right? So because of this, you have a very sweet spot where you should be operating your batteries. Now this is something very important. It's not about thermal runaway alone. It's not about your other thing. It's about trade-off, right? Which you are making at the cell level. Now that's why it's mentioned that you should be operating your battery at certain specific zone. so that you don't lose out the capacity much, you don't lose out the battery life much, right? This is clear. So this is something very important. Now, what happens inside a cell? This is something very important. You should understand why the heat generation is happening at the first place, right? So what happens? This is my anode. In this case, this is graphite layers where my lithium ions are sitting over here. And during the discharge process, these lithium ions migrate from anode to cathode via this electrolyte, right? And there are separators. So all this anode material, all the ions which are stored in the charging process get disconnected from the graphite layer or move. This is for intercalation of lithium ions. They move from anode towards the cathode, right? And the electrons flows through the external circuit. When these ions move in the chemical pathway from the anode towards the cathode, right? There is a resistance in the path, right? Because they have to move there is intercalation which is happening, right? So they have to move between the graphite layers, then they have to move through the electrolyte, then they have to move through the separator, then they have to connect and form the molecular bond at the cathode level again. So they have to travel as a particle from one place to another, right? And there is a concentration gradient also. So all these things combined, when the particles are moving, like imagine a particle which is very moving and very viscous fluid, what will happen that because of resistance, because of friction, the heat generation will happen. Apart from that heat generation by chemical reaction, enthalpy, entropy, right? Those all the phenomena are there, right? Dual will talk about all those phenomena. So this is the basic fundamental. And during the charging process also, what happened? This goes in reverse order. So all these molecules which were bonded with the lithium compound, they get disconnected from this cathode and they move towards the anode and they intercalate in the graphite layers. So during the charging also this phenomena happened, during the discharging also this phenomena happened, right? So this is how the heat generation happened, because you have some chemical reaction which is happening. There is enthalpy change, entropy change, and then the ion movement is also there. There is a friction between the molecules, right, when they are moving. So there are so many phenomena which are happening. This results in heat generation at the first place. This is something very important for you to understand, right? Let's come back. What causes this heat generation? What are the phenomena? So there are two major branches because of which the heat generation happens. Lokesh, you want to say something?
Sorry.
Okay. So there are two things because of which the heat generation happens. One is a reversible process. Second thing is a reversible process, right? Now, irreversible process is divided in further four parts: active polarization process, ohmic losses, mixing process, right? Enthalpy change. And for irreversible process, I think I have, okay, so this is slightly wrong. This should be reversible. I'm sorry for that. There's a typo error. So this is irreversible and this is my reversible. Sorry for the typo, right? And for reversible, there is entropy change, right? So for irreversible process, there is active polarization, ohmic losses, mixing process, enthalpy change. And for reversible process, there is entropy change. What causes this things, right? So why this things happen? Because of charge transfer resistance. Let me use this. Because of charge transfer resistance, right, which is there, because when the charge is getting transferred from one point to another point while these systems are moving, right, this is called active polarization process. When the ions are moving in the electrolyte, right, in the copper collector, in the cathode anode material, that causes the ohmic losses. That is ohmic process, transport resistance phases, right? Then you have mixing process, like when your chemicals are there inside, right, there is a homogeneity inside that. So when how their ions are homogeneously distributed or not distributed, that causes a mixing process that is very negligible in nature. Then enthalpy change because of diffusion of lithium ions inside the graphite layers and then in their cathode material. So that causes some enthalpy change, right? And entropy change is purely from electrochemical reactions. We'll talk about in much more detail. So all this process together increase the it actually results in heat generation, right? Let's see from an equation point of view, right? What are the equations which governs this, right? The typical equation for a heat generation in a continuum process is denoted by this particular equation. So what are these terms? First and foremost is the irreversible heat, right? Which we talked about it. So heat generated from resistive dissipation. So this is the first component. Second component is entropic heat. This is reversible heat in nature, which we talked about earlier, right? This is exothermic during discharge and endothermic during charge. We'll talk about with much more detail in our subsequent slide why this is important. Then you have heat produced or consumed by the chemical reactions whenever the molecules are getting attached to the molecules, detached to the molecules, right? The ions are getting separated during that process. Then there is a heat of mixing, because when the chemicals are mixing with each other, like electrolyte is reacting with your anode material or with cathode materials, and they mix with each other, right? Or SI layer, SCI layers formation is happening. That time this comes into play, right? But normal operating condition, these two things are not so prominent, right? These only things are prominent. And if you see this, V is your actually the terminal voltage, and U is my open circuit voltage. So if you see, V minus U is nothing but your the like voltage drop, which is denoted by the IR also. If you reiterate this equation, that becomes heat generation equals to I square R minus IT du by dt. That is how you get this equation, right? Is this clear? So generally people use this equation, which is your reversible losses, and this is your entropy change, right? There are two prominent heat generation mechanisms which actually operates in normal steady state conditions, right? So, and very important part to note that is the reversible heat source terms is the same order of reversible heat source term. Multiple people ignore this term, but should not be ignored. We'll talk about much more detail, right? And where the T represents your operating temperature, W represents the revolted temperature coefficient, I means operating current, U means the open voltage, P means the operating voltage, right? So we have discussed all day about this. Now let's talk about this resistance, right? Because this is now let's talk about Joule heating first. What is the first term over here? The resistance. Current is any which ways depending on external circuit, but R is my cell resistance, right? So the cell resistance, how does it change? Now, if you see this, if you talk about DCIR, the DCIR changes with respect to temperature, and as the temperature increases, the resistance goes down. We have seen in the first slide also, right? This is the same thing, because the viscosity of electrolyte is less. The Arrhenius equation is also governing the things where the rate of reaction is dependent on temperature, right? So when the reactions are happening faster and there is lesser resistance to the path of ions, so the resistance goes down at lower temperature. Whereas when the temperature goes down, the viscosity of electrolyte increases, density increases, the rate of reaction reduces. That's how the DCR also increases, right? Same thing you can see in the EIS also, electron impedance spectroscopy also. Sorry for that, right? So when the temperature is lower, you see that EIS curve is much more bigger than at higher temperature. This tells you that my DCIR is changing, my resistance is changing with respect to temperature, right? Now the cell resistance also changes with respect to the SOC, right? So if you see this, we have seen this already at higher temperature, the cell resistance is lesser. At lower temperature, the cell resistance is higher. But if you see, it follows a similar graph with respect to SOC. So if my SOC is lesser, right, my resistance is higher. If my SOC is comparatively higher, my resistance is lower. A very phenomenal or a very basic fundamental question comes to the mind. Why is that? Why at lower SOC my resistance is higher, and why at higher SOC my resistance is lesser? So if you see this, a very fundamental thing to note that, let me use pen over here, right? A very fundamental state to note that when the ions are in the anode layer, right? They're intercalated between the graphite layer, right? When the battery is fully charged, right? That time, this is unstable state. So they try to move towards the cathode. So this is my anode and this is my cathode, right? and the ions move from here to here. Now, this is not their natural state. They're always on the highest entropy condition, right? This is not the natural state for ions. They want to move towards this, and there is a higher concentration gradient, right? So when the concentration potential gradient is much more higher between anode and cathode, right? When the battery is fully charged, they want to go to their natural state very fast, right? Because at this point of time, if you represent this, this is unstable state for the ions, right? That is how the self discharge also happens. If you see, if you keep a fully charged battery, after some time it becomes discharged. It never happens ulta, right? It never happens that you keep a discharged battery gets charged. So the charged battery is very unstable, bro. So that from the state of thermodynamics, you always want to come to the lower state of entropy, correct? So if you see that lower SOCs, right, resistance is much more higher because you need to push more energy to move them. But at higher SOCs, what happens? Comparatively at higher SOCs, what happens? Yeah, 1 second. So you can post your questions on the chat. At comparatively higher SOC, what happens? That the ions have a favorable concentration gradient, and they want to move towards this. And there are more sites over here. One fundamental thing which happens after a certain point of time, this resistance again goes up. This happens because all those sites which are there, now they are getting filled with the ions. So now all the, like for suppose 90% ions already moved it over here. Now there is less space for ions to move inside, right? And there is more resistance now. There is more dissolution happen on the electrolyte level. So there's already more crowd now over here. So that's why when the battery is fully charged, right? Or may so sorry, when the battery is fully charged, that time again become difficult for the ions to move further, right? This is the reason it becomes very difficult for ions to move, correct? Now, the heat generation also follows the same thing, right? In the heat generation, if you see, you saw the resistance curve, right? And the I square R losses are very prominent, correct? Over there. So if you see, this follows similarly curve for the heat generation also, right? Where your heat generation is following the same curve as your DCIR, right? But there is a entropic heating also we'll talk about. This is discharge state, right? What happens in that charge state? Your equation becomes slightly changed if you see this, because we talked about entropy change, right? Which is reversible in nature, right? So what happens? The direction of the del u by dt changes in the charge state. So let me show you a graph for that first. So what happens in discharge state if you see the Joule heating, right? Joule heating and the reaction heat, which is your entropy change, follows the same curve, right? So if you this is my reaction heat red color curve, let me put it. So this is my reversible component, correct? And this is my Joule heating, which is my blue color curve, right? What happens that when both are in same order of magnitude, right, and they have same symbol, so you follow this total curve which is over here. But what happened to the charge state? That sign of del u by del t changes, right? Because this is reversible in nature, right? This is not always positive. What happens when this, if you see this color, this curve now, which was reversible heat, the direction changes completely. Although this remains same direction. So the total heat generation direction changes, right? That is how you see this curve over here. Now, this is something very important. If you are only modeling I square R losses, you will not find this curve during the charge state, right? If you ignore the entropy generation, which is a reversible component of it, right? So you'll not this curve. So your heat generation prediction will become wrong during the when the battery is fully charged or when it's fully discharged. Like at this point of time, it's maximum, right, over here. So this is the difference which happens if you're not modeling it correctly. Similarly, what happens, the heat generation also depends on your current rating. Now, you know that it's I square R losses, right? So even if the resistance remains same, your currents goes up, right? So it becomes I square R. So if you see that same is shown over here. So when your current goes up, right, to the battery, I square R losses goes up, and that's why you see very high and regeneration in the battery pack. Something very important to note, uh, uh, this one is that your fast charging process, this heat generation becomes very high because you try to operate at very high C rates, especially DC fast charging, right? And especially this is for the cars, for four-wheelers. People are working towards megawatt charging nowadays. So in the megawatt charging, you have to remove that much heat from the battery. That becomes a very important, right? Similarly, for the charge state also, if you see this same thing is happening, right? So when you from at lower C rate, your heat generation is lesser. At higher C rate is very high, right? For discharge state, the follow the same curve as previously because the shape of the curve remains same, only that becomes expanded in nature, right? This I already explained. Right now, what are different battery modeling approaches, right? So the simple and foremost people know about is equivalent circuit model or empirical modeling or analytical modeling, right? So you have simple RC model, Thevenin circuits, right? Or quantum scale equations which are there to model it in analytical form. Then you have electrochemical model, single particle model, continuous model, heterogeneous model, homogeneous model, particle scale model, ion scales model, which is much more for detailed electrochemistry. Then you have multi-physics model as well. In multiple physics model, what you do is you couple the equations, which is for the electrochemistry, thermal and mechanical. Like for suppose you want to see how my cell expands during the charging or discharging process or in the thermal runaway events. Okay, so in that scenario, you need to have for multiphysics. Otherwise, you cannot estimate what's my impact on the mechanical components, right? So for suppose you have a pouch cell, you want to see how much my pouch cell swells at higher temperature or during the charging process, right? So you need multiphysics simulations for that, right? And especially for thermal runaway events, also you need multiphysics simulations. Okay. Now, so if you see the from complexity and accuracy point of view, the accuracy is moderate, not so low, right? But when you go for multi-physics simulation, it's quite high, right? Because you model the complete electrochemistry, you model the physics completely in 3D environment, right? But from the computation speed point of view, it's extremely slow. You cannot have a very full-scale battery model done the simulation within a few hours, but which is very much possible via electrical model or analytical equations, right? If you see this, the application of this equivalent circuit model is in the embedded application, BMS design, system sizing, when you have to do for the BMS algorithm like SOC algorithm, SOE algorithm, SOH algorithm, right? That time it's helpful. When you have to do some fault management system, these kind of algorithms are important. Equivalent circuit model works because you have very less memory as well as less computation power at your embedded system. So you prefer these kind of things. When you go for complete cell design or battery design or aging simulations or battery health simulation, you go for electrochemical models. When you have to furthermore design a complete cell or battery from mechanical perspective also, or you have to perform the complete detailed system designing, how my system will behave, especially for four-wheelers, when you have very complicated liquid cooling circuits, right? That time how my system will behave. There will be thermal shock or not, how my system will operate when you have too much of vibrations, right? And different DC fast charging condition, especially in megawatt charging systems. That time these things helps the multiphysics models. If you see that from the tool perspective, for the for the equivalent circuit model or empirical models, you use MATLAB, GT-Suite, MSM model. These are 1D tools which helps you, or pseudo 2D also. They help you simulate all these things which is requirement. Then you have COMSOL and GT Autoland for electrochemical models. Then you have for multiphysics model, we have COMSOL, ANSYS, STAR CCM. This is complete 3D simulations, right? So this is the way it works. And you have in COMSOL pseudo 3D also, right? So that way multiphysics is done very well in COMSOL or ANSYS or star CCM, right? This is how you use different tools, right? So if you see, for modeling the heat transfer from the cell to different component, now we'll start understanding a simple lumped battery model first, right? So the heat capacity of a cell, which is MC delta T, right, is equal to heat generation minus heat transfer. So what are the heat generation happening by the cell and how much taking out from the cell, that decides what's my temperature gradient or how my temperature is increasing with respect to time, right? So if you see that heat capacity, if I just change this term slightly, so this is my heat generation term and this is my heat transfer term. By the convective heat transfer, the conduction is not considered. You can add the conduction component also in this if you have conduction components. We'll talk about in much more detail in subsequent slides, right? So this is how you model it. In this scenario, this MC delta T is heat capacity of a cell that decides how my heat its temperature is changing with respect to time. This is my convective heat transfer coefficient or overall heat transfer by convection, by liquid cooling or by air cooling or by something else, right? This is the irreversible heat component and this is my reversible heat component, correct? Now, let's do some hands-on on this now. We have scheduled a demo. So Lakesh will take you through where we build this model and uh, how we have done, like how to simulate this kind of thermal model on a single cell level. Lokesh, over to you.
Yeah, sure. Let me share my screen. Uh, Good morning, everyone. Shall let me know when you see the screen.
Yes, it's visible, Lokesh.
Okay. So thank you for the insights. And so yeah, let me pick from this slide where Vishal was explaining the different modeling approaches. Okay. 2 points to add so that we have the flow into the modeling part, also the MATLAB modeling which we are going to do. So yes, RC modeling, this part is not that complicated thing when it comes to fidelity or run simulation runtime of the model. But the intent is that we have a lighter battery model, and then we have complex algorithms around it. We don't want to put time of our development on something which is not very crucial. So when it comes to algorithms development, it's not very important to know at each and every cell what is the temperature, right? It is like at battery level, what is the temperature, is that much is enough. Knowing the maximum temperature and developing, let's say, safety algorithm around this is enough. But of course, when it comes to designing a battery pack itself, it matters each and every cell how they perform, right? So then we get into a more complex battery model of higher fidelity, right? So in today's demo, we will do RC model, and we will have a feel of how battery thermals work. So we will have a cell model, and then extract some current or let's say power from the cell model, and then we'll see how the heat is generated, how the temperatures are building up, right? So let me share my MATLAB window. We shall just confirm when you see the window,
Yes, Lokesh, visible.
right? So this is our MATLAB interface. I have opened Simulink window here. Okay. So as I said, it will be RC model of a single cell. We don't want to overwhelm some of the people today, but yeah, in our course, which Vishal will be talking about in the end, we will be going till level 3 of the modeling, which let me just re-show the multiphysics model. Okay. Uh, Right. So one more point before I start the modeling part. So when we are developing an electric vehicle, there are multiple teams working on, you know, battery aspects. Okay, and those multiple teams are having multiple models developed, right? So it might sound more sensible to, assign battery modeling to one single team and then give that model to everyone. But then again, that is not the case because the models are different for different teams, right? So they develop it individually. One team is developing RC model, another is doing pseudo 2D model, another is doing 3D model. It depends on what they want to do, right? So this is only one team which works on algorithms, fault management system, understanding at 1D level how battery would behave, and then developing things around that behavior, right? So RC model, very simple approach. We will do three things. Let me put it in this way. One thing would be RC model. I will just put some block. Uh, 1 second. So this is the library section where we have all the block sets we have in Simulink. We'll go to Simscape, okay, because we want to do RC model. One of the ways I do this is to RC model. I will search in this. I'll take one image. Right. So I'll just put this image, and now it is, all we have to do is get these elements and then connect it the way it is there in the image, right? So it is the Simscape section where you have to click on this electrical part, and you will have various these block sets here, okay? Okay, so let me go through this. Foundation library, electrical elements. So capacitor is here, right? We have to get a register. So it's this, right? So putting it in the order it is there in the diagram. Values we will put in once we have the model in place, okay? Or I anyway have the model already ready with me, but we'll make it live also just to have a feel of how we build a model, right?
Okay, so Lokesh, one question came even before you
Hmm.
starting. What someone is asked, what is the RC model? He said did not
Hmm.
follow from the start. So just
Okay,
tell him what is the RC model.
I'll explain what is RC model. For more understanding, we had done one webinar where we talked only about RC modeling. So much more detailed explanation is there in the webinar also. We will share the link. So RC model is nothing but one of the modeling approach. The intent is, see, let's say we want to develop an algorithm which takes care of battery thermals, okay? If the thermals are increasing, we want to modulate the performance of battery, reduce the performance. Now how do we develop that algorithm? For developing that algorithm in this MATLAB window, we need a battery model also, right, which mimics battery's behavior, right? So something which is mimicking battery behavior should be sitting here, and then next to it we will have our algorithm, right? So that we can see how they together are working, right? And then this algorithm which is developed will be put on the hardware, okay? So simple words, we want to mimic battery's behavior. There are multiple ways to do that. RC modeling basically is, so you take a battery or a cell, okay, you draw current from it. So what you see is there is current given by the cell, and there is some sort of voltage behavior at the cell's terminal. All you want to do is you want to mimic this voltage behavior, how the current is taken out from the cell and how the thermals are let's say working in the cell, right? Now this behavior can be mimicked by resistance, capacitance, in some putting when we put them in some combination. This is the combination of resistances and capacitances, which will mimic the cell's current, voltage, and power loss behavior, okay? I repeat, if I put, for example, resistance and capacitance, let's say in this sort of combination, let me just do something, okay? So let's say I do this sort of combination of resistances and capacitance. Here again, I'm not using any extra element. I'm just using again resistance capacitance. This sort of combination will not mimic the cell behavior. Okay. So what we realize is when we put RC in parallel, it is actually also called as time constant behavior. Okay. Again, as I said, details you can refer to our one of the previous webinars, please. So what we understand when we put resistance capacitances in these sort of combination, it mimics cell's behavior. One last way of showing it is, so let's say we have a cell like this. Okay. Yeah. Now if you put a load across it, okay, this is your load, and you demand some current from it. Okay. So let's say the current demanded is this. It is, let's say, negative direction, some, let's say 2 amperes. So what you will observe, the voltage of the cell, let's say it was at 4 volt, it will show this sort of behavior at the terminals. Okay. So intent is very simple. We want to mimic this behavior through some electrical circuit. What we realize is getting resistor and capacitor, combining them in some sort of combination will help us uh, mimicking this character. So this resistance which is there in series is actually mimicking this sudden drop in the voltage. This resistance, series resistance is here. The RC combination, the two RCs which you see is trying to mimic this. And the same is happening when the current is taken back. The series resistance and the RC circuit. Okay, it is doing is it is trying to mimic cell's behavior. So what we are saying in other words is we are making some circuit, forget RC word, we are making some circuit or some model which is behaving like a battery. Okay. Now, in some way we have our battery. Now you can develop algorithm around it. Once the algorithm is developed, you can use this algorithm on your actual vehicle. I hope it is clear. Okay. We'll move on. So yeah, this is how we make model. So I'm just, exactly putting these circuit elements the way it is there in the image, right? What is this? This is DC voltage. Either you find it here, okay, which is actually at this place. But what you can also do is you can just type DC voltage and you will get it like this. Okay. Now, yeah. Now you want to connect some load, right? So for now, for keep just to keep it simple for now, we'll take a load resistor. Okay. And this is how you make a simple RC model. Okay. Now, how to simulate the amount of current you want to draw from it? You can do various arrangements. One of the arrangements is I will put a switch here, and whenever I want to draw current, I will activate the switch. Okay, so again, switch is here only, or you can directly type switch. Okay, there would be multiple switches for this. This switch is required. Right. Activating this, how do I activate it? So people who are very new to Simulink, please don't get overwhelmed. It takes some time, some practice to get this flow in developing anything in Simulink. It's not really that complicated. It's a matter of practice only. So I will use this section, dashboard section, where I have multiple switches. So I am just taking this slider switch. Okay. So this slider switch will be our interface to activate the circuit where current will be drawn. Okay. So how do I do this? Way of doing it is there is something called step source. Okay. Again, where it is in this, there are multiple ways to find it. You can either type step here, and click search, you'll get that here. Okay. Or once you get used to MATLAB Simulink, you will know that at this section in the sources, you have this step signal. Okay. So step signal, I'll connect it like this. Sorry. So one more point to notice, this is very MATLAB specific thing. Okay. It's nothing like a technical thing, these are the block sets which are there in another library, and it is called Simiscape library, right? So these Simiscape library block sets, if you see, they are having, they are in blue color, while these ones are in the regular base Simulink library, black color ones. So an interface is required to connect these two. Okay, so that interface is there in the utilities. PS to Simulink and Simulink to PS. Okay, so in this case, we want to connect from Simulink side to PS. Okay, now either I double click this step thing and then decide when the value should go from 0 to 1 to start the circuit, or what I can do is I will click on this block, I'll go to this connect. Once I click connect, I will click on this step. You can explore what happens when I click before. So MATLAB is quite vast, so it takes time to understand each and everything there in MATLAB Simulink. But yeah, once I do this, a double click on this. Sorry, a single click would turn off the circuit. A single click will turn on the circuit. Okay. How do we know it is connected with the step? I click on this. It highlights this step block. Okay. So very simple. I took an image from Google, the RC image, RC circuit image, and I got those elements dragged, connected, and our circuit, RC cell circuit is there, right? Putting the values, I'll put few of the values later. We'll put, I have already the circuit fully done just to, for the interest of time. So for example, 4 volt is what we want here. So 4 volt we'll put here. Okay. Similarly, series resistance. So it is in ohms. So let's say 25 milliohms, right? So 25 e to the power minus 3. This is how you would put the values, and auto apply is there, so you can directly click on first. So you'll put values for all this. Okay, so now your cell model is there. I'll delete this image now. Now you want to do two more things here. One is circuit will draw current. You want to develop a section where you know how much power is dissipated from the circuit, right? And then that power dissipation, I square R losses or voltage into current losses, you want to use that power dissipation for your thermal part, right? So thermal model would come here. Power dissipation model will come here, right? So power, where all it would get dissipated in the cell for the temperature rise. So of course, we cannot consider the load part, right? Only the cell elements we'll have to consider, right? So it is these resistances from which power is getting dissipated, right? Or heat is getting generated. So what I'm doing is either I do I square R, but in this kind of circuit arrangement, V into I would make more sense. They both are same thing, right? So what I would do is I need to know current. So I would put an ammeter uh, to know the current value. So you have to type current, you get current sensor, right? So you know what is the current flowing through this register, right? Similarly, you want to know current flowing through other registers. Okay, so now I'm just expanding the model. So you see, start with a simple implementation and then add complications in it. Okay, so I'll just again disconnect this part. I need current at this part of the circuit so that I know current through this second register R1, right? Similarly, okay, please bear with me. It takes some time to just keep adding and connecting blocks. Right. I will measure. I can measure current going through the capacitors also, but in this case, we just want I square R losses. If we go to, one stage deeper, these capacitors also have some series resistance which is there, right? Even those capacitors will generate some heat because those capacitors are also some physical elements, right? But for now, these values will ignore, okay? Otherwise, you can put current through this and do I square R losses also. So you can put series resistance equal to 0 at this point. Let me do it for one capacitor 0. And then you can put one more resistor here. Okay. And put that one E minus 6, that is 10 to the power minus 6 value here. So you know what is the heat generated through this capacitor. So you have actually decoupled the internal resistance of the capacitor here. Okay. So just to keep things simple, because we don't have a lot of time for in today's session for the modeling part. So current, I know I need to do voltage into current or I square R. The easier way in this particular circuit is doing voltage into current. So I'll just take voltage sensor also. Okay. So controller, yeah,
Lokesh,
I'll take.
so we have already shown them the RC modeling in last webinar. What if we can take that from there, already the model which you have built, and just show them the thermal modeling aspect of it?
Right.
Can we reuse
Fair
the?
enough, but it's yeah, Vishal, fair enough, but it's anyway done, so I'll not take any hardly half a minute more. Okay, so this is how you get voltage into current, and you have to just uh s- so for one of the part I will do voltage into current calculation. So because loading and another model in MATLAB, it takes time, so that's why I'm just doing it this way now. So this is your voltage, this is your current. You do product of this, you have voltage into current. Okay. Similarly, you have to do for other uh, parts also, where you have voltage across this, current across this, and again voltage across. And then you will add all this. You will understand when I open the already done model. Okay. Now coming to the thermal, so we will assume that already the power loss is coming from this block, okay, to this block. Now we want to develop thermals. Okay, so basic building blocks of thermals, I will again in a different way show how to get all those blocks. If I just search temperature, click here, there are again various ways to do it, but these are some basic building blocks of thermals. Okay, controlled heat flow. Okay, this comes like this. You want some reference temperature source. Of course, you want sensor also, right? What else you want? You want thermal mass of the cell. So you will get thermal mass and temperature source. So this temperature source is nothing but reference temperature. So power will come from this circuit. Okay. It would sit here, the power loss. You have to give some reference temperature here with respect to what temperature, the ambient temperature you can give, or here in this case, absolute temperature, so that whatever power is here, it is compared with an absolute point, right? It is very similar to electrical circuit where it needs, a ground point. This circuit will not run until you put a ground, you put a ground here, okay? So you have to put a ground. Similarly, it is sort of a ground for your thermal model, right? You have this connection for your thermal mass, right? You want to measure the temperature here. Again, temperature to be measured with what reference? You have to give this. So this much of circuit where you are getting power loss. This section you will understand in few minutes. So once you have power loss calculated from this section, it comes here. This building block, controlled heat flow rate source, it will convert that power into a temperature sort of heat form. What is the heat generated? And then that heat generated goes to this thermal mass block, which is of the cell. Okay. With this, the equations which Vishal showed are running in the background, and then heat will be generated, temperature will be generated, right? So we are measuring that temperature through temperature sensor. Okay. Now, just to save time, I will just open a model which is already done. Okay. So let me just, sorry, delete this part. So this is the model already done. You see, across each and every register, I am taking current and voltage, multiplying this is voltage into current, that is power loss across first register, similarly the other register and third register, right? And all this then, I'm adding up here. This is my power loss, right? All the V into Y values are coming at the input, added up, power loss. Going to this part, I have put these values which are with respect to one single cell, okay, mass and specific heat, right? Ignore this section for a few seconds. So this is what we had done, right? We have implemented. So this is already there in place. So what you will see here now is, if I run this model, let's say for 2 hours, 7200 seconds. So the circuit is connected, model will run. So there is some temperature dynamics which is observed through the cell, the rate of the temperature increase. Okay. Sorry, MATLAB at times takes some time. Yeah. So this is how the temperature is increasing. It is starting from 25 degrees centigrade and it goes all the way to, it rises by around 11 degrees in 2 hours. The discharge current in this case is, we can see that single cell, and we are discharging around 3.7 amperes. Okay, so this is around 0.8 C of the cell which we have considered here. Okay, so 0.8 C discharge. Uh, what is the total power loss during this discharge? It's around 0.85 watt. Okay, so 0.85 watt is the power loss when we discharge a single cell at 0.8 C. Okay, and how the temperature is increasing, we have just seen that from 25 degree initial temperature, it rose to 36 degrees centigrade in 2 hours. Okay, now there was a section which I deleted. Now we have to understand why that section was there. This much part of implementation just tells that when you draw current from the cell, because of the heat generated inside, because of the impedances, there is heat generated, and because of that heat generated, temperature is increasing, right? But normally we have airflow, liquid cooling, and many other ways, right? So that will counter that heat generation, and the temperature rise will not be that high, right? Because there will be a counter airflow to you know keep that temperature in check, sort of, right? So it is that section which I had put. This part is trying to mimic the cooling done through air. Okay, the convection heat transfer. So we are putting the values here where it would do some sort of forced air cooling, and that is because the value which we have put here, heat transfer coefficient, it is uh, on higher side. That means it means that we are doing air cooling, forced air cooling. If I reduce that just to have that natural cooling, that value will reduce here. Okay, so what is happening, this block, convection heat transfer block, is connected to this battery thermal mass again. Okay, and of course it needs a reference temperature source, right? So for your understanding, it is ambient temperature here. So what it's doing is, if you just uh, the equations which Vishal showed, there was one place where it was temp minus T ambient, right? So it is that place where you see with respect to ambient how the convection is happening. Okay, so that air cooling is mimicked through this part. So what you would notice is in 70 to 100 seconds, that is 2 hours, without air cooling, the temperature rose from 25 to almost 36. But now with airflow, if I do the simulation, it rose to 31 only, right? Because air cooling is happening. And it's not only the final value, it is also how you control the rate of change of temperature, right? So this is how an air cooled behavior, air cooling behavior on a cell or a battery can be understood. Okay, in this demo, we wanted to keep things simple, so we have taken one single cell, put the values of single cell only, be it the voltage value or the resistances, capacitances value we have put here. Okay, so that's of a single cell, and we have seen how a single cell, when discharged at almost 1 C rate, zero point 0.8 C to be precise, how much is the power uh, dissipated by it, right? Power lost, and that power is not doing nothing but generating the heat, which is through this circuit arrangement. This block takes power as an input and converts that into heat, which goes to the cell's thermal mass block, and that mass block gives output of temperature, right? This connection helps us to mimic the air cooling behavior. Now, of course, if you want to do liquid cooling, there would be, more circuit around it connected to the thermal mass telling the liquid cooling behavior. So it depends on what complexity you want to have in the circuit, right? One more point here is that it is very lumped mass sort of thing. I am not monitoring what would be the temperature at the center part of the cell, at the top part of the cell, at the bottom part, because I don't have to. For me, all it matters is what is the averaged value, because algorithms anyway take some safety margin. I don't want to be very precise, since it is, let's say, a safety algorithm. Knowing an average value at lumped mass level is okay. I will anyway put a safety margin on it and then have my algorithm in place, right? So it depends. This kind of circuit or this kind of modeling doesn't take much simulation time, so that the time saved here can be used for algorithms development. But people who are developing battery uh, or placing the cells, they need to know this particular behavior more in depth, so other modeling approaches are taken. So with this, I would hand it over back to Vishal. I hope you all got a feel of how modeling is done. One of the modeling ways this is, right? RC model. And just for your information, this RC model is so generic that you have thermal model here, right? The highlighted one. You can actually have your SOC model next to it like this, right? The same cell or battery model, you can have your SOC model developed around it. You can have your uh, safety algorithms model developed around it. So this model is very generic and very widely used, sort of universal thing when it comes to algorithms development. Okay. So, and again, for RC model, this is element based implementation. Uh, when you want to understand the dynamics more in depth, you can go into equation based implementation also. Those things we are going to cover in our course, the battery BMS course. So yeah, with this, I'll not take any further time. Handing over back to Vishal. Thank you, everyone. Vishal, over to you.
Yeah, thank you, Lokesh. Thank you very much for insightful model. And I'll tell you, Lokesh had covered in much more detail this same battery modeling in our last session, where we had only the uh, session on the BMS modeling itself, right? So coming back on this, understand this one very important aspect of it. Lokesh has taken you from the single cell, right? But in a battery pack, you don't have a single cell. You have assembly of cells in the assembly level, then module level and pack level. Especially in cylindrical cell becomes much more complicated and very prominent because you have to make now connection with all these cells, right? And how these cells connect with each other. there is some contact resistance, right, between each one of them, because the heat transfer happens from cell to cell as well, right? So if you see this, like for suppose in this scenario, you have columns or three arrays with, or you can say 1, 2, 3, 4, 5, 6 cells in each array, right? Now you have to have a heat transfer between cell to cell also, especially in thermal runaway scenarios, when you want to model how my heat transfer is happening from one cell to another cell, right? Because you are keep trying to keep some PCM material, some heat isolation by mica, right? So it becomes very important you model the conduction and convection accordingly, right? And when you are going with the liquid cooling, things become much more complicated because the heat transfer coefficient now comes into play. Because if the cells are connected like this, you have a heat transfer happening between the cell to the liquid channel and then side to side as well. If the bottom plate is cooled, like for suppose this arrangement, so this is side cooling and this is bottom cooling. In that scenario also, the all the cell comes in contact with the cooling plate via thermal interface material, right? So it's a classical example. For suppose this is similar to a Hyundai Kona vehicle where you on top of it a base plate you have modules, right? So this is my see Temp material below which my cooling channels are there. And for suppose if a liquid cooling is flowing towards this, right? It gets divided into cooling channel, different cooling channels, right? It passes through that, and the the hot coolant comes out from this area, right? So this is how it works. And if you see a particular cross section, how does it work is a particular cell module, consider this is a prismatic module or pouch cells below which there is a thermal paste. Same holds true for bottom plate cooling of your cylindrical cell also, which I showed the image earlier, right? So there is a cell, there is a thermal interface material, thermal paste, whatever, and there is a cooling channel, right? So how do we model this? So if you see the typical heat generation happens from module, it goes to thermal paste, then it goes to the cooling channels, right? This is how it happens. So if you see again, if I break this down, so you have a heat generation from the complete cell, which is getting passed to the thermal paste, which is getting passed to the battery plate of aluminium, then it getting passed to the coolant. If you see a circuit level diagram of this, you have a thickness of this thermal paste, right? You have a thickness of this aluminum plate and you have a coolant, right? So at a circuit level, you have the paste conductive resistance, which is already there over here, right? Then you have plate conductive resistance, right? Then you have a heat transfer coefficient, which is coming by these component, right? So this is conductive resistance and this is convective resistance. You have to model all these components cell by cell or module by module. That depends on the discretization which you are doing on the simulation level, right? And what's the level of accuracy you want at the battery pack level? You want a cell level accuracy or you want a model pack level accuracy? So depend on discretization which you are doing. So this is for a single cell or a single module, you can call it, right? If you want to see in much more detail, there was a old video which we published around 2 years back on the same topic, understanding battery thermal module, a liquid cooling part of it. You can watch this video in the same YouTube channel what we have. I think this is the first video which we launched that time 2 years back on this channel. So you can watch it over there. Okay. Now, let's talk about what is Techlanz. We're already running late now. So we conduct these kind of things, right? So let's talk about what is Techlanz also now. I think you have learned a lot during this session. You learned many new concepts, how the things work out, right? So Techlanz, if you see, is a unified ecosystem for electric vehicle development. We have training programs. We provide industrial projects, right, on the real hardware. We provide engineering services. We conduct these kind of webinars on technology trend and knowledge sharing also. We have a global community for engineering also, where you can join. We'll share the link also with you in the chat section. So you can join and brainstorm on those electric vehicle ideas if you have any, right? You can join us, visit our website and all those things. And one thing like to tell about our courses also, if you are interested to learn more about such things in a structured courses format, you can stay in this session and we'll talk about the courses what we have. So the course which is running live right now is Battery Plus BMS Bootcamp. It's already running, where we are taking learners from cell level to the battery pack level learning, where we deep dive into the cell fundamentals, cell testing, cell modeling, the way we have shown you over here, right? Then we do the BMS hardware design, PCB designing, component selection, circuit simulation, schematic designing. We deep dive and teach you on the model-based development, associative algorithm development, cell balancing, production algorithms. We teach you also the firmware design process, microcontroller data sheet, communication protocol, base firmware design. Then we teach you the battery pack design also, because at the end, whatever you saw today, it's a part of a battery pack design, right? Because you have to design a battery pack. It comes under the algorithm development also, but at the end you have to design a battery pack as well, right? We cover multiple projects on cell modeling, BMS PCB design, SOX algorithm, BMS firmware design, circuit simulation, and we use multiple tools because at the end it's skills. Knowledge is everywhere now, but we provide skills in our training program. This is something we strive for. At the end, you should be doing the things on hands-on. That's what we want. That's